So how can we predict chemical reactivity? Let's have a look at the thermite reaction here. This is where aluminum reacts quite vigorously with iron 3 oxide. We want to know why it doesn't work the other way around. So you can see myself, Scove, and Thornton here. This is what we do when you guys are gone in June. So, as you can see, the thermite reaction proceeds with a huge energy release, which might cause you to start thinking about an enthalpy diagram and may get you thinking, okay, with such a large enthalpy value, does this reaction, would this be an example of equilibrium? And we can see that just by the observation there, this is not going to be an equilibrium setting. This reaction goes one way only. It makes metallic iron and aluminum oxide. There's a huge release of energy here, so there's a very large negative value for delta H, which you can infer just from that observation alone. We don't even need to work anything out with numbers, all right? But absolutely we could. So, is there a way that we could predict that this is what was going to happen? That this reaction would occur as written rather than the reverse process? Simply by looking at looking at what was involved. So I'm going to draw a representative enthalpy diagram here, showing a significant activation barrier, and then I'm also going to show a significant value of energy release. So this is my negative delta H down here. All right, this isn't to scale. All right, but this is the idea. What I'm trying to show here is that the activation energy for the reverse reaction here would be absolutely enormous, all right, due to the significant activation energy for the forward reaction, coupled with the additional release of enthalpy. So there's no way that this reaction goes backwards. All right, so is there something that I could do by saying, will aluminum replace iron, or will iron replace aluminum in a single replacement type reaction? So yes, obviously there's something that we can do here. All right, but just to clarify what I'm really trying to ask. All right, the thermite reaction works as written there in white. All right, the alternate question, or the question is, why doesn't it work, or is there a way that I can identify how this doesn't work if I was to write it iron plus aluminum oxide? You're going to want to use the activity series, which is table 25 in your data booklet. All right, and if you were provided with this scenario, you can use this the activity series to determine which of the two reactions will proceed as written. So iron plus aluminum oxide, or aluminum plus iron 3 oxide. You know that both of them don't work. So how can I use a data set to tell me which one will work? So now you saw the blurb on the screen there. This series is only for single replacement reactions, right? So what you're going to want to do is identify both of the metals involved. So I find aluminum and I find iron in the activity series. Aluminum is higher up in the activity series than iron. Okay, what this means is that aluminum, so metallic aluminum, elemental aluminum, can take the place of iron that's already in a compound, right? And that will yield free iron and aluminum in a compound. All right. You could say the converse as well, is that aluminum being lower in the iron is lower in the activity series than aluminum. So a reaction in which iron would take the place of aluminum that's already in a compound does not occur. All right, so this is a handy little way to identify which reactions will work and which won't, without having to resort to the standard reduction potentials table, which we will examine in a little while. But this can be just a little bit of a quicker method.